With the decline of symmetric encryption algorithms for private message encryption, new cipher suits have come into the light. The glaring issue with symmetric algorithm was key exchange. Having to pass secret keys is a risk in its own right, now that we are unable to solve in all the scenarios. Thankfully, the DSA algorithm has managed to solve this problem. The use case for this cipher is rather niche but crucial nonetheless. While the DSA algorithm is exclusively used for verification and transmission of signatures, the RSA algorithm can be used for general data encryption and decryption as well. Functioning on a similar public key cryptography architecture, it is seen as a more complex solution to bolster security. Let's take a look at the topics to be covered today. We first get a recap on what asymmetric encryption is and how is it any different from symmetric encryption. We learn what digital signatures are and how they are used in today's world. Next, we understand the digital signature algorithm and see how it works step by step. Moving on, we learn about the advantages DSA provides when it comes to managing digital signatures in a corporate environment. Next, we understand the RSA algorithm and see how it works from a layman's perspective. We understand how RSA can be used to encrypt and decrypt general data apart from digital signatures. And finally, we learn about the advantages RSA provides when it comes to managing digital signatures and encrypting information. Let's take a look at asymmetric encryption. Asymmetric encryption uses a double layer of protection. There are two different keys at play here, a private key and a public key. The public key is used to encrypt the information pre-transit, and the private key is used to decrypt the data post-transit. This pair of keys must belong to the receiver of the message. The public keys can be shared by a messaging, blog post, or key servers since there are no restrictions. As you can see in the image, the two keys working in the system. The sender first encrypts the message using the receiver's private key, after which we receive the ciphertext. The ciphertext is then transmitted to the receiver without any other key. On getting the ciphertext, the receiver can use his or her own private key to decrypt the information and get the clear text back. There has been no requirement of any key exchange throughout this process, therefore solving the most glaring flaw faced in symmetric key cryptography. The public key known to everyone cannot be used to decrypt messages, and the private key which can decrypt messages need not be shared with anyone. The sender and receiver can exchange personal data using the same set of keys for as often as long as possible. In this example, we have two people, Nancy and John. If Nancy wants to send a message to John, John's public key should be used to encrypt the information. The ciphertext is then transferred to John, who can use his private key to decrypt the data and get the plain text back. This goes to highlight how we have overcome the problem of key sharing when it comes to asymmetric encryption. Now that we have a proper revision, let's understand what digital signatures are before moving on to the algorithm. The objective of digital signatures is to authenticate and verify documents and data. This is necessary to avoid tampering and digital modification or forgery of any kind during the transmission of official documents. They work on the public key cryptography architecture with one exception. Typically, an asymmetric key system encrypts using a public key and decrypts with a private key. For digital signatures, however, the reverse is true. The signature is encrypted using a private key and is decrypted with the public key. Because the keys are inked together, decoding it with the public key verifies that the proper private key was used to sign the document, thereby verifying the signature's provenance. Let's go through each step to understand the procedure thoroughly. In step 1, we have M, which is the original plaintext message, and it is passed on to a hash function denoted by h hash to create a digest. Next, it bundles the message together with the hash digest and encrypts it using the sender's private key. It sends the encrypted bundle to the receiver, who can decrypt it using the sender's public key. Once the message is decrypted, it is passed through the same hash function hhash to generate a similar digest. It compares the newly generated hash with the bundled hash value received along with the message. If they match, it verifies data integrity. In many instances, they provide a layer of validation and security to messages through a non-secure channel. Properly implemented, a digital signature gives the receiver reason to believe that the message was sent by the claimed sender. Digital signatures are equivalent to traditional handwritten signatures in many respects, but properly implemented digital signatures are more difficult to forge than the handwritten type. Digital signature schemes in the sense used here are cryptographically based and must be implemented properly to be effective. They can also provide non-repudiation, meaning that the signer cannot successfully claim that they did not sign a message while also claiming their private key remains secret. Further, some non-repudiation schemes offer a timestamp for the digital signature so that even if the private key is exposed, the signature is valid. To implement the concept of digital signature in real world, we have two primary algorithms to follow: the RSA algorithm and the DSA algorithm, but the latter is a topic of learning today. So let's go ahead and see what the digital signature algorithm is supposed to do. Digital signature algorithm is a FIPS standard, which is the Federal Information Processing Standard for digital signatures. It was proposed in 1991 and globally standardized in 1994 by the National Institute of Standards and Technology, also known as the NIST. It functions on the framework of modular exponentiation and discrete logarithmic problems, which are difficult to compute as a force brute system. Unlike DSA, most signature types are generated by signing message digest with the private key of the originator. This creates a digital thumbprint of the data. Since just the message digest is signed, the signature is generally much smaller compared to the data that was signed. As a result, digital signatures impose less load on processors at the time of signing execution, and they use small volumes of bandwidth. DSA, on the other hand, does not encrypt message digest using private key or decrypt message digest using public key. Instead, it uses mathematical functions to create a digital signature consisting of two 160-bit numbers, which are originated from the message digests and the private key. DSAs make use of the public key for authenticating the signature, but the authorization process is much more complicated when compared with RSA. DSA also provides three benefits, which is the message authentication, integrity verification, and non-repudiation. In the image, we can see the entire process of DSA validation. A plain text message is passed on to a hash function where the digest is generated, which is passed on to a signing function. Signing function also has other parameters like a global variable G, a random variable K, and the private key of the sender. The outputs are then bundled onto a single pack with the plain text and sent to the receiver. The two outputs we receive from the signing functions are the two 160-bit numbers denoted by S and R. On the receiver end, we pass the plain text through the same hash function to regenerate the message digest. It is passed on to verification function, which has other requirements such as the public key of the sender, global variable G, and SNR received from the sender. The value generated by the function is then compared to R. If they match, then the verification process is complete and data integrity is verified. This was an overview of the way the DSA algorithm works. We already know it depends on logarithmic functions to calculate the outputs. So let us see how we can do the same in our next section. We have three phases here, the first of which is key generation. To generate the keys, we need some prerequisites. We select a queue which becomes a prime divisor. We select a prime number p such that p-1 mod q equal to 0. We also select a random integer g which must satisfy the two formulas being mentioned on the screen right now. Once these values are selected, we can go ahead with generating the keys. The private key can be denoted by x, and it is any random integer that falls between the bracket of 0 and the value of q. The public key can be calculated as y equal to g to the power x mod p, where y stands for the public key. The private key can then be packaged as a bundle which comprises of values of p, q, g, and x. Similarly, the public key can also be packaged as a bundle having the values of p, q, G, and Y. Once we're done with key generation, we can start verifying the signature and its generation. Repeat. Once the keys are generated, we can start generating the signature. The message is passed through a hash function to generate the digest H first. We can choose any random integer k which falls under the bracket of 0 and q. To calculate the first 160-bit number of our signing function of r, we use the formula g to the power k mod p into mod q. Similarly, to calculate the value of the second output, that is s, we use the following formula that is shown on the screen. The signature can then be packaged as a bundle having r and s. This bundle along with the plain text message is then passed on to the receiver. Now with the third phase, we have to verify the signature. We first calculate the message digest received in the bundle by passing it to the same hash function. We calculate the value of w, u1 and u2 using the formulas shown on the screen. We have to calculate a verification component which is then to be compared with the value of r being sent by the sender. This verification component can be calculated using the following formula. Once calculated, this can be compared with the value of r. If the values match, then the signature verification is successful and our entire process is complete, starting from key generation to the signature generation all the way up to the verification of the signature. With so many steps to follow, we are bound to have a few advantages to boot this, and we would be right to think so. DSA is highly robust in the security and stability aspect when compared to alternative signature verification algorithms. We have a few other ciphers that aim to achieve the simplicity and the flexibility of DSA, but it has been a tough ask for all the other suits. The key generation is much faster when compared to the RSA algorithm and such. While the actual encryption and decryption process may falter a little in comparison, a quicker start in the beginning is well known to optimize a lot of frameworks. DSA requires less storage space to work its entire cycle. In contrast, its direct correspondent, that is RSA algorithm, needs a certain amount of computational and storage space to function efficiently. This is not the case with DSA, which has been optimized to work with weaker hardware and lesser resources. The DSA is patented, but NIST has made this patent available worldwide royalty-free. A draft version of the speculation FIPS 186.5 indicates that DSA will no longer be approved for digital signature generation, but it may be used to verify signatures generated prior to the implementation date of that standard. The RSA algorithm is a public key signature algorithm developed by Ron Rivest, Adi Shamir, and Leonard Edelman. Their paper was first published in 1977, and the algorithm uses logarithmic functions to keep the working complex enough to withstand brute force and streamlined enough to be fast post-deployment. RSA can also encrypt and decrypt general information to securely exchange data along with handling digital signature verification. Let us understand how it achieves this. We take our plaintext message M. We pass it through a hash function to generate the digest H, which is then encrypted using the sender's private key. This is appended to the original plaintext message and sent over to the receiver. Once the receiver receives the bundle, we can pass the plaintext message to the same hash function to generate a digest, and the ciphertext can be decrypted using the public key of the sender. The remaining hashes are compared. If the values match, then the data integrity is verified and the sender is authenticated. Apart from digital signatures, the main case of RSA is encryption and decryption of private information before being transmitted across communication channels. This is where the data encryption comes into play. When using RSA for encryption and decryption of general data, it reverses the key set usage. Unlike signature verification, it receives the receiver's public key to encrypt the data and uses the receiver's private key in decrypting the data. Thus, there is no need to exchange any keys in this scenario. There are two broad components when it comes to RSA cryptography. One of them is key generation. Key generation employs a step of generating the private and the public keys that are going to be used for encrypting and decrypting the data. The second part is the encryption and decryption functions. These are the ciphers and steps that need to be run when scrambling the data or recovering the data from the ciphertext. You will now understand each of these steps in our next subtopic. Keeping the previous two concepts in mind, let us go ahead and see how the entire process works, starting from creating the key pair to encrypting and decrypting the information. You need to generate the public and private keys before running the functions to generate ciphertext and plaintext. They use certain variables and parameters, all of which are explained. We first use two large prime numbers which can be denoted by P and Q. We can compute the value of n as n equal to P into Q and compute the value of z as P minus 1 into Q minus 1. A number E is chosen at random satisfying the following conditions, and a number D is also selected at random following the formula ed mod z equal to 1, and it can be calculated with the formula given below. The public key is then packaged as a bundle with N and E, and the private key is packaged as a bundle using N and D. This sums up the key generation process. For the encryption and decryption function, we use the formula C and M. The ciphertext can be calculated as C equal to M to the power E mod N, and the plaintext can be calculated from the ciphertext as C power D mod N. When it comes to a data encryption example, let's take P and Q as 7 and 13. The value of N can be calculated as 91. If we select the value of E to be 5, it satisfies all the criteria that we need it to. The value of D can be calculated using the following function, which gives it as 29. The public key can then be packaged as 91,5 and the private key can then be packaged as 91,29. The plaintext, if it is 10, which is denoted by M. Ciphertext can be calculated with the formula C equal to M to the power E mod N, which gives us 82. If somebody receives this ciphertext, they can calculate the plaintext using the formula C to the power D mod N, which gives us the value of 10 as selected as our plaintext. We can now look at the factors that make the RSA algorithm stand out versus its competitors in the advantageous topics of this lesson. RSA encryption depends on using the receiver's public key so that you don't have to share any secret key to receive the messages from others. This was the most glaring flaw faced by symmetric algorithms, which were eventually fixed by asymmetric cryptography structure. Since the key pairs are related to each other, a receiver cannot intercept the message since they don't have the correct private keys to decrypt the information. If a public key can decrypt the information, the sender cannot refuse signing it with his private key without admitting the private key is not in fact private anymore. The encryption process is faster than that of the DSA algorithm. Even if the key generation is slower in RSA, many systems across the world tend to reuse the same keys so that they can spend less time in key generation and more time on actual ciphertext management. Data will be tamper-proof in transit since meddling with the data will alter the usage of the keys. The private key won't be able to decrypt the information, hence alerting the receiver of any kind of manipulation in between. The receiver must be aware of any third party who possesses the private key since they can alter the data mid-transit, the cases of which are rather low. Hope you learned something new today. If you have any questions from today's session, be sure to let us know in the comment section below. Subscribe to our channel for more videos like this, and thank you for watching.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.